So, you know, we had a little bit of chapter 5 on the previous test. So that stuff won't be on there. The stuff where what's the sign of the work, that sort of thing, or you have a force acting over a certain distance for over a certain angle, that sort of thing won't be on the exam. But of course, work is a big part of that chapter 5. So in chapter 5, we have the work-energy theorem. That just says that if you do work on an object, you change its energy. That comes up in a couple different ways. Like if I have a force over a displacement, so if I have a force that acts over a certain displacement, that can change its energy. It can change its kinetic energy, or it can also change its potential energy. And you'll sort of know that from the context of the problem. So if I have an object and I'm pushing it in this direction with a certain force over a certain displacement, if I do work on it, it's going to increase the kinetic energy. Whereas if I lift something in this direction, I'm changing its potential energy. I think you'll see from the problem when you see problems like that. So that's the work-energy theorem. Also, of course, you'll see conservation of energy. I'm pretty sure that you have the problem where you have like a bead on a track or a cart on a track, that sort of thing, and asking the velocity or the position of the cart at particular times. I know you have one of those. I think you have a couple problems actually based on that. And I'm pretty sure too that you also have a spring. We can look at both of those problems in just a bit, but on those problems, you need to be able to ask yourself, what is the energy at particular points? So for example, if I have a cart here that has a velocity equal to 0, make sure you read the problem, okay, because it'll say in the problem whether velocity is 0 or not. I try to make it clear in the figure, like I don't want anybody to miss a question just because they read it wrong. I want you to miss it because you don't know how to do it. I want you to get it right because you do know how to do it. But anyway, so I try to make it as clear as possible. And, you know, in the test, if something's unclear to you, feel free to raise your hand. You know, often students ask me questions, and I just tell them, sorry, I can't tell you that. But if it's something that I can just clarify, then I will absolutely do that. So if you feel like something's unclear, please ask me. So anyway, conservation of energy. Here, for example, I would only have potential energy. I'd have no kinetic energy because the speed is 0. Down here, I would only have kinetic energy because h is 0, so potential energy is 0. And here, for example, I would have both potential and kinetic energy. And then a similar thing with the spring. If I'm at my equilibrium position right here, my elastic potential energy is equal to 0. My kinetic energy is at its maximum. If I'm at some other position, say over here, where the spring is compressed, I have potential energy, and that's equal to 1/2 kx squared. Okay, so you'll have conservation of energy, work-energy theorem. You need to know conservative versus non-conservative forces. Non-conservative forces don't conserve energy. Conservative forces do conserve energy. Non-conservative forces are like friction. Non-conservative forces are also path dependent. Conservative forces are path independent. Okay? We can come back to that if that's unclear to you, okay? Well, let's go on to chapter 6. That's all of chapter 5. I think that's right. Yeah. Chapter 6 is on momentum. You have two big classes of problems. You have those problems where you say F is delta P over delta T. And then you have those problems where you say the initial momentum is equal to the final momentum. You should also go through the various concept tests and stuff and make sure that you're up on sort of the idea of momentum and what is momentum and how we use momentum. You'll be able to tell these problems apart because on these problems on the left, these impulse problems, it'll talk about a force. And that'll be sort of the key distinguishing feature. Now, you need to read the question carefully because sometimes I might ask about the force, sometimes I might ask about the change in momentum. So make sure that you're answering the question what it's asking. That's generally true. So we can work through a problem like that in just a second. You will have a collision where the momentum is conserved, and on this, there won't be any mention of force. There are forces involved, of course, right, when you have these collisions, but we won't really talk about them, that they don't really come into the calculation at all. So this is conservation momentum. Again, we'll come back and work through a problem like that. And you need to know elastic versus inelastic. In elastic collisions, we conserve energy and momentum. Both energy and momentum are conserved. Some students remember this because of the E, that you have an E in both elastic and energy. I don't know. I remember it because an elastic collision is really bouncy. Elastic is bouncy. And in really bouncy collisions, you conserve energy. But whatever you need to do to remember, that's fine. In inelastic collisions, only momentum is conserved. Inelastic momentum is conserved in any collision. Anytime you have a closed system, momentum is conserved. Uh, Inelastic collisions are basically anything, cars colliding, people bumping into one another. Anytime you have two objects that touch one another, that's an inelastic collision. An elastic collision is anytime you have conservative forces that are acting, field forces. So charged particles, for example, coming together. They're elastic. They conserve energy because they don't actually touch. Okay, so you need to know those. I think there are probably just one question about that. All right, and then chapter 6 or 7 rather. And the test is pretty well distributed between the 3 chapters. There might be one or so fewer questions from chapter 7 than the other two, but for the most part, it's about 8, 8, and 8, 8, 8, and 9, or 8, 9, and 8, something like that. There are about 20. There are 26 questions, and then there's one extra credit for chapter 7. Okay. Um, Chapter 7 is on rotation. You'll have one or two kinematics problems where you're using these equations. The theta equals omega naught t plus 1/2 alpha t squared. Omega equals omega naught plus alpha t. These are basically, you need to be able to read the problem and figure out what is omega, what is alpha, what is t, what is theta, and be able to solve for whatever it is that you're looking for. One-step problems, nothing too complicated, except you just have to be able to read the problems and know what is what. And that does take some skill. So you need to be able to use these equations to solve problems. We can look at one of those from one of the old tests. You'll also need to know how to convert between the various angles. So remember, 1 revolution is 360 degrees, is 2 pi radians. Don't forget that when we're talking about angular displacement, that clockwise is negative, counterclockwise is positive. You can remember that from your unit circle because the unit circle goes in the counterclockwise direction, which is the positive displacement, positive angular displacement. That's in radians. Be very careful with your units on this. That's where students always mess up because sometimes I might give the value in revolutions and you need it in radians. Just make sure that the entire test, make sure that you read the units and be clear on what it is that I'm asking for and what the units are given. So rotation, kinematics, what else was, centripetal forces. So centripetal forces and centripetal acceleration. Centripetal acceleration is v squared over r. And then also centripetal force, just by Newton's second law, is mv squared over r. Remember, this is the force that causes a circular motion, that causes an object to move into a circular path. That force is always towards the center of the circle. That force causes the velocity of the vector, the velocity of the object, to change not magnitude, but to change direction constantly. So it's a scenario where we have an object moving with constant speed, but also constant acceleration, because it's always changing its direction. And we described that acceleration with the centripetal force. We had several problems that we worked through, like we had the car going around the curve. In that case, the centripetal force was the static frictional force. So we had the static frictional force was equal to the centripetal force, or rather, the static frictional force is the centripetal force. Right? It's just a class of forces that cause circular motion. And in this case, that centripetal force is the static frictional force. We had a problem where we had a ball on a string going around. In that case, the centripetal force is the tension on the string. We also, I don't know if we worked a problem like this. I don't think y'all seen one, but where you, like the fair ride, right, the spinny thing, where the normal force, you know what I'm talking about? We talked about this in the in-class section, but the fair ride where you go squeeze up against the wall and it spins you around. You know what I'm talking about? Yeah, so in that case, you have a force that's pushing on you into the circular path, and that force is the normal force, the wall pushing onto you. So the centripetal force is really just a type of force, and it's going to be a different force in each scenario. It's the force that causes circular motion. And that's it. That's all the major topics. Any particular chapter that y'all want to deal with, or should I start with chapter 5? Start with chapter 5. Okay, so chapter 5 again is let's work in energy. Let me pull up a couple of different examples. So this is fall 10, fall 11. Okay, so this is a good work energy problem. This is fall 2011, exam 2. Did I start the recording? I did. All right, this is fall 2011, number 2, and it says a force of 1 Newton pushes a block over a rough flat surface at a constant speed of 2 meters per second, pushes a total distance of 8 meters. What is the power used to produce this motion? I forgot to mention that, but power is work or energy over time. These things are on your equation sheet. Make sure that you're familiar with your equation sheet, by the way. You might want to print it out if you haven't, and just sort of look over it. There are a couple things that aren't on there. I'll show y'all at the end that. But most of the stuff is on there, and this thing is on there. All right, so I first want to find the energy or the work that's done. I have a force of 1 Newton. Um, it moves over a distance of 8 meters. So the work is 1 Newton force times the distance, which is 8 meters. It does 8 joules of work. And then I also need to know, well, what time was required to do this? So my time is the distance over the velocity. And that's sort of our basic kinematics definition. Velocity is distance over time. So time is distance over velocity. V d over t. And so I can solve that for t and get that. So time is distance over velocity. The distance is 8 meters. Velocity is 2 meters per second. So that's 4 seconds. So in this case, my object has a power equal to 8 joules over 4 seconds, which is 2 watts. Notice we could also ask a different question. What is the, oh no, I can ask that here. Okay. Um, you okay with that one? Let's go back a little bit. That wasn't exactly what I wanted to do. Let's go back and look at conservation of energy here. This is problem number 13, exam 2, fall 11. You throw a ball up in the air and it goes to a height of 16 meters. What is the speed of the ball when it's at a position of 8 meters? You can see a problem like this are like the cart problem. These are similar. They work basically the same way. You work them out the same way. In this one, I throw it up. It goes up, comes back down again. It goes to a height of 16 meters. And I want to know what is the velocity at 8 meters. So this is h equals 8 meters. And I want to know what its velocity, what its speed is. So I want to think about the types of energy that it has at particular points. At the top, potential, kinetic, or both, at the very top. Only potential, because at the top it has a speed of 0. So at here I only have potential. Here in the middle I have potential and kinetic. And down at the bottom, only kinetic, because h equals 0. Be able to look at a scenario and ask yourself, how is the energy distributed? The total amount of energy is always the same. So I can say that the potential energy here equals the sum of the energies here. That is mg times 16 meters, that's the potential energy at the top, is equal to mg times 8 meters plus 1/2 mv squared. Notice that the masses all cancel. I can divide through by m and get rid of the masses. I can take my 8g over, and I get 16g minus 8g equals 1/2 v squared. Listen, on your algebra, be very careful. I don't want you to go too slow, but you need to be deliberate about doing your algebra, because I know that a lot of you, you're okay at algebra, but it's just sort of a little weak when you're in a rush and in a test. So just be deliberate about it. Don't hem and haw about it, but be deliberate. So write out the steps if that helps you. I divide both sides by a half here to get rid of the half. That's 16g minus 8g divided by a half. 8 divided by a half is what? It's 16. It's not 4, right? It's 16. So this would be 8 over a half, which is 16g equals v squared. And then I square root both sides. So it's the square root of 160, which is, what was that, 13? Okay, yeah, so 13 is the right answer. Um, you will have a problem like that. Actually, you know what? It's a cart problem, but they work the same. We can look at, you want to look at one of those? Cart problem? They work out exactly the same. Can I clear this? Any questions? Listen, if this is too fast, please just slow me down. I don't want to go too fast, but we have a lot of material, so I want to make sure that we at least hit the highlights. Okay? All right, let's look at that other exam. I think there was a cart problem there. I guess there wasn't. Let me pull another exam. Fall 12. And 3, fall 12. No? Shoot. Hold on. Okay, like this one. This is fall 14. I think, no, we haven't seen this one. We might have worked this one in class. So here I have a particle on a frictionless track. That tells you that energy is conserved because it's frictionless. If you have a track, it's going to be conserved, so don't sweat that. It's at initial height of 10 meters and is not moving. So here I know that I only have potential energy. I know that because the speed is 0. And I'm asking for what is the speed of the particle at point B. Here I have potential and kinetic energy. I know that because some of the potential now has converted into kinetic energy. And I want to know what is the speed. So again, this works out the same way. I say that the potential energy over here equals the potential energy plus the kinetic energy. And then really it works out the same way from the previous one. I'm just going to set it up and I'll leave it at that. So I have m times g times 10, that's this height, equals m times g times 2 plus 1/2 mv squared. Noticing that my m's cancel, which is good because I don't know the mass, and I solve for v. Okay, can I stop there? It's just like the previous problem. Let's look at number 13 because I'm pretty sure, I'm not absolutely certain. I forget if I put a spring problem on there, but I'm almost certain that there is a spring problem. So if I'm almost certain, then you could be almost certain too. But I'm not certain, so don't get on the test and be upset with me if there's not one on there. Okay, so a spring has a spring constant of 100 Newton meters. The mass of the block is 2 kilograms. You compress the spring, causes the block to move to the right, and then the block leaves the spring and continues on the surface. What is the block after it leaves the spring? So what happens here is I have this block. I compress it away from its equilibrium position by 10 centimeters. Watch your units, okay, because this is in centimeters. You'll need to convert it to meters. I compress it by 10 centimeters, and then it causes the block to come over here, and it gives it a velocity when it leaves the spring. It's going to give it all of this elastic potential energy, which will convert it into kinetic energy. In this case, we work it in a very similar way as that previous problem, but I say initially I only have elastic potential energy, and that is all converted into kinetic energy. So that's 1/2 kx squared equals 1/2 mv squared. And then in this case, I'm looking for the velocity of the block or the speed of the block. I cancel out the halves. I just multiply both sides by 2. That's what happened to those. And then I solve for v. Divide both sides by m. I get kx squared over m. And then take the square root of both sides. So it's the square root of kx squared. Let's see, k is 100. X is 0.1. So that's going to be 0.01. 100 times, that's 1 divided by the mass with the square root of a half. What is it? 0.7. Okay, so D is the right answer. Okay, being careful, couple of, let me put the numbers in there. So it's the square root of 100, that's K, times 0.1 squared, that's X, converting to meters, divided by the mass, which was 2 kilograms, right here. I'm pretty sure there's a problem like that. Also, don't forget that Hooke's law comes into play here too. I could also ask you, what is the force? If I have this block and I push on it, I can ask you, what is the force? I know what K is. It's 100 newtons per meter. I've compressed it by 0.1 meters, so my force is going to be what now? 10. Right. So it's going to be F is kx or negative kx. That's by Hooke's law. That is on your equation sheet. It'll be negative 100 times 0.1. Actually, my displacement is in the negative direction, and so my force is 10 newtons. You know, the negative, you can leave it off if you want. Usually I'm just asking for the magnitude of the force anyway, but if you do encounter something like this, think about the figure. Like I could look at this figure, and I know that if I compress this spring in this direction, the spring is going to be pushing back in this direction. So if it does come out, think about it before you just, jump at the number. Usually if I am asking for the direction, I'll have both positive and negative options on there. So just think about what is the direction of the spring. Okay? How y'all feel about chapter 5? Okay? Any particular questions about chapter 5? You're not going to see any of these about plus, minus, zero work. You will see things about how does the work or how does the energy change if you change this or that. What happens to the energy? Yeah. All right. We move on to chapter 6. We can come back to chapter 5 if y'all want at the end if we have time. So chapter 6, remember you have two big classes of problems. You have the conservation of momentum, of which you have a couple, and then you also have the impulse problems. And then you look back at the concept tests and all the various conceptual questions about momentum, what it is, what its units are, all that jazz about momentum and the role that it plays. Let's see. Oh, here's a good basic collision problem. Make sure you know your collisions too, okay? Elastic versus inelastic. I do ask you about the difference between elastic and inelastic. So here I have an inelastic collision where momentum is conserved. I have a 1 kilogram block traveling to the right at 3 meters per second. I have a 2 kilogram block that's initially stationary. The 2 kilogram block now picks up a speed of 1 meter per second to the right. And I want to know what is the speed of this block. I'm assuming that it's to the right. We actually don't know if it's to the right or, oh, those are all to the left, aren't they? I'm sorry. Let me redraw these. Oh, shoot. This is all messed up. I'm sorry. So my 1 kilogram block is traveling to the right. So my 1K is traveling to the right at 3, and it collides with a 2 kilogram block that's stationary, and then the 2 kilogram block is now at 1 meter per second, and I want to know what is the speed of this block. So I have an initial and a final state. This is my initial, this is my final. I say the momentum in the initial state is equal to the momentum in the final state. Okay, you with me? What about your signs? Okay, make sure that you get the signs right. In this case, it's all positive, but I'll tell you right or left. And remember, right is positive, left is negative. So be very careful with your signs on this, especially chapter 6 and 7. The signs often trip up students. So my initial momentum is just the product of these two, 1 kilogram times positive 3 meters per second. It's going to equal to this 2 kilograms times 1 meter per second plus 1 kilogram times V. So I have 3 minus 2 equals V. V equals 1 meter per second. It's going to be to the left or right? It's going to be to the right because it's positive, right? Okay? That's a good basic collision. You will have one of those. I think you have a couple. Okay? Y'all could do that right now, couldn't you? This thing right here? Okay, so I'm saying the initial momentum equals the final momentum. Remember, the momentum is the product of mass and velocity. So this is the mass of the 1 kilogram block times its velocity, which is 3 meters per second. Remember, there's another term here that's unwritten, and the value of that term is 0. It's the momentum of this block, because the momentum of this block is 2 kilograms times its speed, which is 0. So I didn't write that term here because it's 0. I just left it out. Okay, and then over here I have the momentum of the first block, 2 kilograms times 1 meter per second. This is the second block actually, 2 kilograms times 1 meter per second plus 1 kilogram times the velocity that we didn't know yet, so this. And then I solve for V. Initial momentum equals final momentum. You have two objects that are colliding. Okay? Let me give you a little hint. So, let's say that I have a guy. Y'all seen this movie, The Martian? The Martian? No, I haven't seen it. I read the book. But in The Martian, he uses things to make him go in space, right? Like if you're out in space, you find yourself out in space and you need to get somewhere, the way you do that is you throw stuff in one direction and then that forces you back in the opposite direction. Okay? Like, I think he like cuts a hole in his suit and it shoots air in one direction and it propels him back. Like a jet engine. That's how jet engines work. Conservation momentum. So if he is sitting here and he starts and he throws an object in this direction, say a 1 kilogram object with 2 meters per second, it's going to make him go back in the opposite direction with the same momentum. So let's say he's 50 kilograms, then to get 2, it's going to be like, it's going to be 50 kilograms times V equals 1 kilogram times 2 meters per second. So that would be V is equal to 2 over 50 meters per second. Y'all with me on this? Yeah, it's sort of like we had the cannon problem on the concept test where the cannon shot a bullet in one direction and it went back in the other direction. Well, now imagine what if instead of throwing one block, one kilogram block, he threw two 1 kilogram blocks. So he throws one and then he throws another one. What's his final velocity going to be? It's going to be the sum of both of them. So instead of being 2 over 50 meters per second, it's going to be what? It's okay. No, it's going to be, yes, I think what you're saying is right, but let me try it. It's going to be 4 over 50. Like if he throws one, he gets up to 2/50 meters per second. If he throws 2, he gets up to 4/50 meters per second. And if he keeps throwing things, it's going to increase his speed each time. Follow me on that? So, like, for example, with our cannon problem, with it shooting cannonballs in one direction, if I shoot more than one cannonball, I just add up the momentum, just like here, where if he throws more than one object in one direction, it's going to shoot him back in the opposite direction, just multiplicative. That you'll just, it would be negative, yeah. Okay? Are clear on what I'm saying here? I see about 3 nods. Yeah, sort of, kind of. Okay, think about it. Just imagine the cannonball problem, but instead of shooting one cannonball, I shoot a whole bunch of cannonballs. What does that do to my velocity? My velocity increases a lot by however many cannonballs I've shot. So if I shoot 10 cannonballs, I go 10 times as fast. If I shoot 100 cannonballs, I go 100 times as fast because I get 100 times the momentum. Okay? That's just a hint. Not something. Okay. Let's see. So what was that? Oh, so now that is a conservation momentum problem. Let's look at an impulse problem. And again, how are you going to know the difference between these problems? Whether they ask for force or whether the force is mentioned. Like I might not be asking for the force. I might ask for something else, like the change in momentum or the time that it occurred in, something along those lines. But force will come into there at some point. And in that case, you know that you'll need to use the impulse formula, which is really Newton's second law. F is equal to delta P over delta T, which is M delta V over delta T. Okay, so what you need to be careful here with is your signs, because when I have a rebound, that is when I'm going in one direction and then I go in the opposite direction, you have to be very careful with your signs, because often students will look at this and they'll say, well, the change in velocity is what? It's 3, but that's wrong, right? The change in velocity is actually 10, because, let's see, 3.5 is my final velocity. V initial is 6.5. But if I imagine I'm throwing it down onto the floor, so my initial is actually negative, and my final, which is coming up, is positive. And so my delta V is going to be V final, 3.5, minus a negative 6.5, divided by the change in time, which is 0.1 seconds. All right, so this is the mass, 0.15 times 10, divided by 0.1, that's 1.5, so it's going to be 15 newtons. This is true too if I'm going in a horizontal direction and my initial is positive and my final is negative. But my suggestion to you is that you just don't worry about the signs at all. That when you encounter a problem like this, instead of taking the difference in them, right, instead of saying 6.5 minus a negative 3.5 and trying to mess with all the signs, if you have a rebound problem, you just add up the velocities. Okay, don't worry about the signs. Don't worry about any of that business. It doesn't really matter what the sign of the force is, because I'm never even going to ask you what the direction of the force is. And even if I do, you can sort of think about the scenario and say, well, the force is in this direction. But I'm not going to ask about the direction of the force. Okay? You just add up the speeds. So here you just say 6.5 and 3.5. And don't worry about all those signs and stuff. Okay? You aren't going to miss that because of the signs? Okay, please don't. A lot of students will. So I don't want that to be okay. Can I clear this? Those are two big classes of problems in momentum. Conservation of momentum and these impulse problems. Let's see. You need to know momentums of vector. Um, energy is a scalar quantity. We had some concept test questions. You need to know about your inelastic versus elastic. Energy is conserved in which of those? Elastic or inelastic? Huh? Elastic, right. Right. And in these, right, the gas particles colliding, right. So elastic collisions, that's really the only good example. Anytime you have charged particles that are coming together, those are elastic collisions. There aren't really many true elastic collisions. Um, but every other collision is an inelastic. Um, some students have been a little confused because we talked about a subset of inelastic collisions. Those were called perfectly inelastic. And a perfectly inelastic is just when they stick together. I don't even know why they call it that. I guess because they stick together or whatever. But a perfectly inelastic is just when they stick together. It's just an inelastic collision. So don't be too confused about that. It's just when they stick together. Okay? You'll have some questions about if the velocity changes, what happens to the energy, what happens to the momentum, or if the mass changes. Make sure that you know how to work with those problems, and make sure that you know the formulae for those quantities. All right. Anything on this test or in this chapter, chapter 6? No? You feel pretty good about chapter 6, chapter 5, chapter 7 then? Y'all look tired. Are you tired? You look tired. Okay, let's look at chapter 7 then. So chapter 7 really, kinematics, couple problems. In fact, you know what, your extra credit problem is a kinematics problem. It's not an easy problem, but if you have a little extra time to spend on kinematics, you can spend it there. It's worth your effort. And but there are some kinematics problems within the test as well that are simpler. Also have the angles, the directions of the angles, displacement, definitions of displacement and velocity, translating linear quantities to angular quantities, right? That was that S equals theta r, V equals omega r, A equals alpha r, and then centripetal forces as well. So let's look, let's see here. I think one of these had some good questions on it. Okay, here we go. Like here's a good basic conversion problem. I have 8.3 revolutions per second. Convert it to radians per second. Remember our unit conversions. Those are not on the equation sheet. I think most of you probably know them, but some of you, they might be a little new to you. In one revolution, I have 2 pi radians. 8.3 times 2 pi. 2 pi is about 6, so it must be 52. 52 radians per second. Just know those unit conversion factors. Units, 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 right? What's my advice to you? The first thing is what? Don't go to jail. The second one is what? Check your units, right? So don't go to jail and then check your units. Okay? Um, here's a good, I think we had a homework problem like this. This is a problem where we have to consider what is our centripetal force? I have this car going around a curve. The centripetal force that holds the car on the road and makes it go in a curved path is the static friction. And I want to know what speed can I round that curve? Well, my static friction needs to be big enough to keep me on the road, and so it needs to be big enough to provide the centripetal force. Remember, my static friction is mu mg. That's not on your equation sheet, but it's from chapter 4, but you might need to know it. Mu mg is mv squared over r. I know r, I know mu, I'm looking for v, so I solve this for v. Notice the mass cancels. That's good because that speed they post on the curve doesn't matter if you're a big old honking truck or if you're one of those little smart cars. It's not dependent upon your mass. So I'm solving this for v, cross multiply, mu gr, square root of that, 0.7, 10, 50. Square root of about 400-ish. Is it 19? Yeah. So A is the right answer, 19 meters per second. Okay. Let's look at some kinematics problems. You will have a centripetal force problem, one or two, I forget, a couple problems probably. And then also, again, all the basic stuff about centripetal forces. They act towards the center of the circle. Uh, they cause the direction to change, the velocity, the velocity vector to change direction constantly. I'm going to go back to that actually. Let's see if there's, oh, let's look at a kinematics problem. Okay, here's a kinematics problem. This is a pretty good indicator of what you'll see. Again, fairly straightforward, one-step problems. You need to be able to read the problem and know what it is that you're looking for. So I'm looking, I have a couple things. Starts from rest. That tells me omega naught. It moves through 10 radians. That tells me theta. In 2 seconds, that tells me t, before reaching its final angular speed. That's omega. So I'm looking for omega. Remember my equations. I have theta equals omega naught t. It's 1/2 alpha t squared. Omega equals omega naught plus alpha t. So which one am I going to use, the first or the second? Now I'm not going to use the first because it doesn't have omega in it at all, in fact. So I know theta. Theta you don't really need in this problem. Just sort of threw it in there because, you know, that's the kind of guy I am. But I'm going to use omega, the second one. I say omega equals omega naught. That's 0. Uh, wait, no. I do have to use. Right, yeah, okay. I have to use the first one to find alpha. Sorry, who said that? I shot you down. Was that you, Kristen? I'm sorry. Told you that's just the kind of guy I am. So I use theta is 10 radians. Omega naught t is 0 plus 1/2 alpha 2 seconds squared. I solve this for alpha is equal to 5, right? No, half of 4 is 2. Yeah, 5 radians per second squared. And then I come over here and I use that here. So I have 5 radians per second squared times t, which is 2 seconds. And so omega is 10 radians per second. Uh, that's a little more difficult than you'll see. I tried to make it as simple as possible because we haven't been on chapter 7 for a really long time. Okay? But if you can do this problem, you'll be fine. Y'all can do this problem? Remember, guys, or ladies, excuse me, uh, it's it's um you might think that you know how to do it, but make sure that you're doing it on your own without any help from anybody, to just to make sure that you really know what you're doing, because you know you can sit and watch somebody do it all the time, but you only really learn it when you sit down and do it yourself. Okay? Do that with the homework, do it with the old test. I have those solutions there for you to go back and check, but you really learn it when you sit down and do it by yourself. Okay, let's see. So did kinematics. Make sure that you, things like this, sort of exploring the idea between linear and angular velocity. Remember, on a rotating object, the angular velocity is always the same. The linear velocity, however, on a rotating object is different. It's dependent upon the radius. So those linear and angular quantities are related. S is equal to theta r, V is equal to omega r, and the tangential acceleration is alpha r. That's different, by the way, than the centripetal acceleration. The centripetal acceleration occurs when you're moving at a constant speed. The tangential acceleration occurs when your object is actually speeding up as it rotates, when you have an alpha. This is a good test. Here's about tension, sort of basic idea. What can you say about the force of tension on the ball? Is the tension tangent to the circular path? Yeah. Yeah, I should know this. Okay, this is sort of our basic ideas about centripetal forces. So if I have a ball that's going around on a string over my head, right? There are some things about centripetal forces, about that force. The tension is the centripetal force. Is the centripetal force ever tangent to the circle? It's always towards the center, right? It's always towards the center. Is this true? B? Yeah, that B is right. Let's look at these. It acts away from the center. No, that's not it. So the answer here will be B. You might look at a problem and think, gosh, I don't know this, but just sort of take a big deep breath, because you probably do know the answer, and you probably know it really well. Just read it, and just take a big deep breath. All right, I think that's all for chapter 7. Make sure that you're up on sort of your relationships. If you change one thing, how does that change the other thing? We had a bunch of questions like that. Let me show you the equation sheet just to point out some things that you may or may not have. Hopefully you're a little bit familiar with it, but this is it. We had a lot more equations on these chapters. That's why I give you an equation sheet. But don't let it lull you into some false sense of security, because usually knowing the equations is not really the hard part. Knowing the equations is just sort of the icing, or sort of the very beginning of stuff. Would like you to notice that I have this expression for the centripetal force, but remember, if I plug this in for V, I get an alternate expression, which is m omega squared r. Might be useful for you to know that. I'm not saying that like as a hint, wink, wink, or anything. I forget if that's useful on this test or not, but sometimes it's useful. But if you forget that, not a big deal. If you know V, or if you know omega rather, you can always calculate the speed V just by multiplying it times the radius. And also Hooke's law is on there. Yeah, I think that's really all I wanted to point out. Okay, just sort of get familiar with it so you know what's on there. It'll be on the back of your form, the equation sheet, so I'll print it out for you to bring. Any questions or last minute things? Okay. Okay. Let me see. Okay, so a tire is placed on a balance machine. Okay. Y'all want to see it? Yeah, so it says a tire 1 meter in diameter is placed on a balancing machine where it is spun so that its tread is moving at a constant speed of 20 meters per second. A small stone is stuck in the tread of the tire. What is the acceleration of the stone as the tire is being balanced? Let me draw a picture for this. Was this from the quiz? Yeah. All right, so I have a tire. So this is my tire. I have a stone that's stuck out here. It says that it's a diameter of 1 meter. That means that the radius then is 0.5 meters. Because the radius, it says that it's spun so that it's at a constant speed of 20 meters per second. So V has a magnitude of 20 meters per second, but that's okay. The speed is 20 meters per second, but it is accelerating, right? Because the velocity is always changing direction. Um, and I want to know, what is the acceleration? Well, the acceleration is not equal to alpha r, because alpha is equal to 0. That would be the tangential acceleration anyway. But I know that it is accelerating. That acceleration is our centripetal acceleration, which is v squared over r. So v is 20 squared divided by the radius, which is 0.5 meters. So it's 400 over 0.5, which is 800 meters per second squared. You have 800 here. Oh, okay. Did you get it right on the quiz? Oh, okay. Did you put 800? Oh, right, yeah. You know what? All the questions on your quizzes, they're from old exams. I've told you this before. Yeah, I told you. Yeah, don't sweat it. I'm gonna pad the quiz numbers. Okay. All right, Kristen, is that okay? Well, it's not fair. Man, me too. Listen, I do all these translations and what for like these Greek translations, and then I just learned I spend 10, 12 hours a week like translating 12 verses. It takes a long time to translate these things because you got to look at every word. And I just learned that there's a website that has all the answers on them, and like all the other students been using the websites, and I feel really gypped. I feel like an idiot actually. Nobody told me. Right. Okay. All right, ladies. Is that all? Listen, not an easy test, but it's probably the easiest test all semester. So I want some really great grades on it. Yeah, I don't want to lull you into thinking it's easy, but it is the easiest.